Okay, let's go ahead and get started. So as always, welcome everybody to our bi-weekly community Zooms at the Green Bank Observatory. And thank you guys very much for taking some time out of your day to learn a little bit about some great science going on with the telescope. As always, we'll start this off with a little bit of news what's going on here at the observatory, and then we'll move into the science presentation by Charles Romero, who will be talking about the thermodynamic evolution of galaxy clusters. So what's going on with the observatory? Of course, COVID is on everybody's mind still, unfortunately. Number of COVID cases within the state of West Virginia is staying steady at a very unfortunate 10% of all tests. Number of vaccinated people is starting to go up a little bit, but only ever so slightly. We're at about 51% of the state is now at least partially vaccinated. Within the county itself, you see a very similar situation, about 29 active cases this week. So that's the bad news. So the good news is, though, on site, we're fully back to work. Today is September the 1st. So that means we've returned to full operations with all staff here on site. All the staff are, of course, vaccinated on site or have an accommodation, a legal accommodation, and a work plan in place. We are, though, still doing health checks every day. So as everybody comes in, we just make sure that they're healthy and ready to work. And of course, are requiring masks in any common area just due to the growth of variants with COVID-19. Nonetheless, it's still great to see everybody back on site and feeling like a busy place, which is nice to see. Telescope, of course, remains in regular operation. We're still in the middle of summer maintenance. We still have our telescope inspections. These are triennial inspections going underway, painting going on, the annual repairs, and preparing to do our track week when we go and inspect the track on the GVT and replace any wear plates that need replacing. The Science Center, of course, has reopened. It's been open for a while now. We're slowly increasing the number of ways people can come in, both through bus tours and also just through the exhibit hall itself. And of course, masks are required there as well. And equally as exciting, we have visitors coming back on site. We've got observers coming on site. We've got the single dish school coming up. So all of that is going on. We do require that all visitors give us advance notice that they're coming so we can prepare for them. And of course, require all visitors to be vaccinated and to go through the same health checks as the rest of the staff. We do have lots of job openings on site. We're interviewing for these, but some of them are still out there: software engineers, digital engineers, and all sorts of other things. So if you're ever interested, or you know somebody interested in working at the observatory, please take a look at our website and go to our careers page, and you can see all the different fantastic opportunities that we have for people at all walks of life. And then, of course, I want to just mention we're continuing our biweekly Zooms. These have been fantastic for us to get to hear about great science, and it's encouraging to see so many different members of the community calling in and listening to these talks. After this talk, our next one will be with Manuel Fonseca at West Virginia University, and then Steve Croft at Berkeley will be talking at the end of the month. With that, just a reminder to everybody, our single day school and observer training workshops are coming up the week of September the 13th. This will be a hybrid school. We're trying out the idea of both in-person and remote options, something that if it goes well, we might continue well into the future. The sign up for this one is closed. If you missed it, if you couldn't get into the observer training, I know it was full. Don't worry, we'll have the next observer training early on in the calendar year of 2022. And the notice about that will be out. And of course, we'll have a single dish school again next year. So with that, I'll thank everybody again for being here and hand this off to Jay to introduce today's speaker.
Okay, thank you. Today's speaker is Charles Romero from the Harvard-Smithsonian Center for Astrophysics, and he is going to be speaking on insights into the thermodynamic evolution of galaxy clusters. And if you have questions for Charles, please submit them on the Q&A button on the lower right of your screen. Okay, Charles, take it away.
Great, thanks for that introduction. Let me get my screen shared. All right. There you go. So as Jay said, I'll be talking about insights into thermodynamic evolution of galaxy clusters. In particular, we're looking at evolution as inferred from recent observations of IDCS 1426. So just to get us started, a quick outline. I want to do a very quick motivation as to why study the evolution of thermodynamic profiles. and then spend a fair bit of time on what we expect to see for these profiles. Then I'll get into the profiles themselves of the galaxy cluster and our subsequent inferences on the evolution of those profiles and conclusions. All right, so why do we care about the evolution of galaxy clusters? Well, one of the primary motivations of studying galaxy clusters in general is to constrain cosmological parameters from cluster counts. So how many clusters of a given mass at a given redshift do you have? And obviously, the expected counts will depend on how you expect your clusters to evolve, both in the sense of just how is mass evolving, but then also observationally, how are you relating whatever quantity your observable is dependent on to mass. From an astrophysical perspective, obviously the processes that go on in the intracluster medium, the ICM, can be of interest. Or maybe you're also interested in just interactions of galaxies and wanting to know what the thermodynamic properties are of the ICM that the galaxies are interacting with. All right, so what do we expect? I would say the short answer is self-similar evolution. And that has been postulated from pretty far back. I'd say Press-Schechter is one of those initial papers that gets us started on this idea, playing with this idea of Gaussian density fluctuations. But you don't strictly need to assume that. The bigger thing is if you just have non-radiative gravity, or gravitation, and not worrying about radiation, you'll often come out with a self-similar evolution. And so a lot of these toy models get started with this Einstein de Sitter universe, or just matter only. And we'll see that's a pretty good approximation, even in the concordance model. A few things to note. I've got a few equations about Press-Schechter, but we probably don't need to pay too much attention to that. I think for reference, if anyone's not a galaxy cluster person, the mass of a cluster we define by a mass within a certain radius relative to the critical density, so a density contrast. And the typical choices are 2500, 500, and 200. 200 is just a nice round number close to 180, where again, if our toy models kind of got started with this Einstein de Sitter universe, then it turns out 180 would be where you get your virial radius. All right. And on the right are a top hat model showing kind of way back just a top hat density contrast early in the universe, still that way at turnaround. And then later when it's actually formed, either at z equals 0 or z equals 0.5, some non-top hat distribution of matter. All right, another quick refresher. A lot of these quantities will scale with some power of E of z. And so it would be good just to have roughly in mind what E of z looks like for the concordance cosmological model. Here's a plot for most redshifts we'd be interested in. All right, so getting into some profiles. Here, actually, before we get into thermodynamic profiles, let's look at just matter, total density. And there's a lot going on here. I'll start with the left plot. The dashed lines are unscaled density, and the heavy solid line is z equals 0. And so these other lines go towards higher redshift. So that means at higher redshift, the central density was greater. Bear in mind also, we do have scaled radii. It's not that the clusters evaporating completely. But the interesting thing I would like to point out is, at least against my own intuitions of how something would gain mass, you would think the density everywhere kind of increases. That's not so much the case for galaxy clusters. Your central density is actually decreasing as you go forward in time. Now, the other thing to point out with these plots is, okay, how do we want to scale that density depending on our universe, that is Einstein de Sitter or concordance cosmology model? You could consider to scale relative to critical density and this delta of Z. This paper, again from Boehringer et al., is going to call this variable density scaling. Or on the right, you could have a fixed density scaling, so just critical density. And you see there, that's roughly an agreement. But as they get into later in their paper, you can do a slightly better scaling of the density to get self-similar profiles. Another conclusion from this is that their model that they're playing with is the recent formation approximation, I guess, and that may not be so great for concordance cosmology. Just to reiterate this with a more modern simulation that we end up using in our paper, Andrea and all, 2021. Here again, we have a mass plot, and you see that the density is, well, almost the same at those inner radii, but at lower redshift, the density does increase at large radii. And again, here, I would say the big difference is that now the x-axis, the radii, is the physical radii, and we're not doing any scaling. So it's a bit perhaps easier to see how that density is increasing at large radii. All right, and this simulation does incorporate a fair bit of radiative physics. Whoop. Not what I want. All right. All right. Then specifically, we can also look at dark matter particle location. This again will show roughly the same conclusion as that profile plot, but perhaps in a slightly different way. Ultimately, you see that this black line for fixed R over R500, you're not keeping the same density at those scaled radii, but for fixed radii, it's roughly the same until you get out fairly far, say 500 kiloparsecs. Okay, what to conclude about self-similarity? Well, you certainly can get self-similar profiles, but that's not to say that that's tracking what individual particles themselves are doing. And yes, self-similarity has its applications and utility. But it depends a bit on your cosmological model, and potentially if you're really assuming recent formation, there's dependence on when your cluster collapsed. Another thing right here is from a recent review paper, Walker 2019, also shows that you have a choice of what you want to scale to. So it's not just, say, critical density that you could scale to. Even in a concordance cosmology universe, you could choose to scale to a matter density. So here on the right, R200M would be a radius where your density contrast is relative to matter density strictly. And so an interesting paraphrase that I came across in another reviewed article is that nature appears to do accounting relative to mean mass density and dynamics relative to the critical density. So adding that onto our conclusions about self-similarity, it does matter your choice of radius or density contrast relative to matter or critical density. All right, now I will shift a bit more into the thermodynamic profiles and what we've actually seen. Again, from this review paper, we'll start with a pressure profile. And here the black curve is this A10 or universal pressure profile, which is a fairly canonical self-similar profile. And again, one thing we'll have with these thermodynamic profiles is they're scaling their like P over P500, or every quantity will have some 500 just scalar that it's divided by, and that will be related to generally M500 to some power and E of Z to some power. So you see that overall, all of those clusters together, I would say, yeah, that looks fairly self-similar. There's a fair amount of scatter. Here, there's more scatter. And your entropy will scale slightly differently again with those quantities. Back, okay, here to electron density, so not quite total matter density. That too is not too distant from self-similar expectations. And then temperature profiles. So what can we make of thermodynamic profiles as observed? That first thermodynamic profile, the pressure profile, I would say had the least scatter of those we looked at. But the scatter potentially argues that, okay, self-similarity isn't the full picture, and that may not be too surprising. There's certainly deviations from, say, hydrostatic equilibrium, that it's not unreasonable to expect deviations when we're not in a purely gravitational universe. So in order to create those profiles, though, you have to keep track of self-similar scalings, both radially and with a normalization. And that, well, self-similarity definitely is very useful for cosmological applications. But if you're just trying to envision how the galaxy cluster is changing with time, it might be a bit more difficult to keep track of how, say, P500 and R500 are changing as well. But I also note here, one could consider scaling your P500, K500, whatever, as a function of f of z here, which is E of z times delta of z to the 1/2. That was at least put forward in that Boehringer paper. So we'll revisit evolution in a bit, but first I want to get into the thermodynamic profiles that we recover for our cluster of interest, IDCS 1426. And to start off with here, I'll look at the pressure profile that we get from Mustang 2. Actually, let me also highlight the left image is what we see with Mustang 2. There's a clear point source there. And then the right is X-ray surface brightness or counts. Okay, so our Mustang 2 profile looks, I would say, fairly reasonable there, but it's not as high in pressure at the center as you might expect from an A10 fit. Also, I'll note that the mass, we don't do a strict mass derivation in this work, but it's consistent with previous estimates of 2.5 times 10 to the 14, which is fairly massive, I would say very massive for the redshift of the cluster. All right. Then, since we have X-ray data, we can look at the profiles we would get from X-ray data alone, which are shown on the left here, electron density, temperature, and pressure. And we'll do two avenues of fitting these quantities. One is a physical fit where we've constrained the dark matter to an NFW profile and assume hydrostatic equilibrium. And the other is a descriptive fit, just assuming some parameterization, but no imposition that there's hydrostatic equilibrium or a certain dark matter profile. All right. And so, well, let me go back here also to note, okay, the density profile, either case is very much in agreement. The pressure profile, the red line is actually the SC profile, but both X-ray fits are in fairly good agreement there. Whereas the temperature, nominally there's still an agreement, but you can see the physical fit tends to show an increase of temperature more than, say, the descriptive fit. Even so, going forward, when we combine SC and X-ray, we'll see that, yeah, the density profile is going to be really dominated by the X-ray constraints, but the temperature profile will very much increase with radius, where the SC is imposing its greater constraint on that pressure at large radii. Here too. And the red line here now is comparing to another cluster at a very similar redshift. And you can see then the contrast that this cluster, IDCS, has quite a bit greater temperature than expected, even, well, certainly relative to something like an A10 profile or canonical temperature profiles, but even relative to this specific cluster. All right, so to get into the evolution of IDCS 1426, we want to then compare to a plausible present day descendant. And to do that, we look at what the expected mass evolution is from z equals 1.75 till today. And you see that the respective increase would say today it should be above 1 times 10 to the 15. And given that mass, we can compare to, say, the average profiles given in a recent paper that goes out to large radii, this XCOP sample, Ghirardini 2019, with an average redshift of 0.07. And before getting into our actual evolution numbers, first of all, we'll be introducing this evolution parameterization, which looks at a fixed radius, or just in physical radius rather than unscaled. And what does it mean for zeta greater than 0 or less than 0? So greater than 0 means it was greater in the past, and vice versa. And in particular, I would say, now that we're looking at physical radii and not scaling them, you don't necessarily expect that your zeta equals 0, even for a universal pressure profile in the case of the plots on the right, but just generically, any self-similar profile isn't strictly going to have zeta equals 0. And so to gain some intuition for what you might expect, I've shown a few different masses. In particular, the curve of most interest is the orange one of proper evolution, where you have the mass of our cluster of at z equals 1.75 and the greater mass at present day cluster. But just to have some extra information, just if you had no mass evolution according to M500 anyways, you would still have some non-zero zeta. All right. That primer aside, if we actually go into numerical simulations to gain greater perspective on what we should expect, you get plots on the right. Again, these are from the magneticum simulations. And you see that there's definitely some similarity between our evolution profiles on the left and those on the right. So even the pressure, you've got a pretty similar, roughly linear slope here, perhaps not as steep as in the magneticum simulation, although actually those plots also go a bit further out in radius, so have some caution there. But I think the most unique evolutions we're getting are where there's obvious discrepancies with the simulation. So for instance, the temperature and entropy evolutions. All right, so I guess this will jump a bit quickly into the conclusions, but the density profile is roughly as expected. It doesn't evolve in more central radii, but at the extremities of the cluster, you are still accreting mass. So you're gaining in mass, not just say because R500 would grow on its own with the critical density decreasing with time, but you are in fact accreting more matter. However, the temperature and entropy profile were greater than expected at large radii, and this excess of temperature and entropy must be transferred inwards as the cluster evolves. Even though that temperature excess could also be seen as a manifestation of excess pressure at z equals 1.75. In fact, the pressure still increases as you go forward in time, just because you are gaining more material. You should expect the pressure to increase with time to a modern day or present day descendant. All right, a little bit more on the conclusions, interpretations, and future prospects. Here we didn't have the resolution to further resolve what physical processes might be causing these deviations from expectations. Again, actually, even though I'd say the more prominent feature is the excess of temperature at large radii, we also had slightly lower pressure than you might expect from A10 in the center. So this could be due to bubbles, say from a central AGN in the cluster, or even sloshing. Meanwhile, the larger temperature at large redshift would plausibly be due to shock heating of infalling gas, even if you expect that to happen beyond R500, perhaps that heating transferred within R500. So ultimately, we, and I think many in the community, still want to observe more clusters at this very large redshift range and see, is this a more common phenomenon or is this rather unique to this cluster? So with that, I'll end and take questions.
Thanks very much, Charles. We have time for a few questions. Please submit them using the Q&A box to the lower right. I'm not seeing any questions in here just now, but I do have a question, Charles. Looking at the Mustang SCE image, it really is dominated by that point source.
Yes.
And you feel that you can remove that effectively enough that it doesn't influence or give exceptionally large uncertainties in the actual SCE.
Yeah, that's right. So we have pretty good constraints on the beam shape itself, and pointing accuracy is pretty good. So between a direct removal, well, ultimately, we don't just remove it, we do mask a region very central to the point source, and then we add a greater uncertainty in the outskirts, say the secondary beam of the air beam. We adjust our uncertainty in the pixels accordingly.
Mhm.
So
Okay. Well, I'm not seeing any questions coming in. So Charles, let me oh, here we go. Is the high temperature at large radii at all similar to what we see at much smaller scale when looking through the solar corona?
I'm not sure what's being intended there. Okay, obviously the solar corona does heat up a fair bit from the photosphere, but I think the physics are substantially different in those cases, that I wouldn't want to draw too much of a connection there.
Mhm.
Is that?
Okay. Okay, well, thanks very much, Charles. And I'd like to remind everyone that we will be having another one of these sessions in 2 weeks. And at that time, we'll hear from Emmanuel Fonseca of West Virginia University on measuring the radius of a high mass neutron star. Thanks for attending and look forward to seeing you then.